In the previous lecture, we were discussing how to write solutions of second order differential equation with constant coefficients, second order homogeneous, second and higher order linear homogeneous ODEs with constant coefficients. We have discussed three cases. In fact, I told you that there are three cases for the second order differential equation. The case one was real and distinct roots. In case of second order differential equation, case two, we discussed when there are real and repeated roots. Case three was complex conjugate roots. So we discussed the first two cases for second and higher order differential equations. Today, we are going to discuss case three, how to write solution of second order and higher order ODEs, linear homogeneous ODEs with constant coefficients in case if we have complex conjugate roots. So first of all, as previously we discussed, if we have a second order differential equation, which might be a2 y double dash plus a1 y dash plus a naught y is equal to 0. So this is our equation. In general, a2, a1, and a naught, they are constants. They are any real constants. Now, after writing this equation into the operator form, a1d plus a naught times y equal to 0, we write characteristic equation or polynomial, characteristic polynomial, which is basically, I told you, in short, we can just replace d by m. But in detail, we assume that y is equal to e raised power mx is the solution of this differential equation. By inserting this solution into this equation, we obtain that characteristic polynomial. I hope you know it. So it is a2 m square plus a1m plus a naught equal to 0. Now this is a polynomial equation. How to find the root of a polynomial equation? We can use the quadratic formula, in fact, which is minus b is in fact minus a1 plus minus square root of b square minus 4ac divided by 2a1. So in fact, if this discriminant, the term of this square root, if this is less than 0, okay, if the third case appears, this case 3 appears when we have this discriminant term less than 0, a1 square minus 4ac. If this term is less than 0, then this polynomial equation must have complex roots. And complex roots are, in fact, they always exist in pairs. In fact, we call them complex conjugate roots. Those roots are conjugate of each other. So we assume that that polynomial equation have two roots, alpha 1 plus iota beta 1, and M2 is alpha 2 minus iota beta 2. Okay. So in fact, we can write them only in alpha as well, because they are complex conjugate of each other. So we can write them in this way as well, because they are, the real part is same and imaginary part is same as well. So M1 and M2 are alpha plus iota beta, and M2 could be, sorry, must be alpha minus iota beta. So these are two complex conjugate roots of the given equation. And in fact, these are two distinct roots. Now, how do we write the solution in case of distinct roots? Then the solution of given ODE 1 can be written as, y of x is what? A constant times C1 times e to the power what? Alpha plus iota beta times x plus C2 alpha minus iota beta times x. Okay. In a similar manner as we had written for the case of real and distinct roots. Now this solution can further be simplified by using this identity, e to the power iota theta is equal to what? It is cosine of theta plus iota sine of theta. This identity, basically, you must have studied this identity in your maybe A-level or intermediate mathematics. So basically, we use it when we convert the Cartesian coordinates into polar coordinates. I hope you know it already. So e to the power iota theta, iota is what? Iota is square root of -1. I assume that you already know it. And wherever this iota comes, we assume that that number is a complex number. Now, using this identity, we can simplify this solution. How can we simplify it? In fact, here we have this y of x. You can write it here e power alpha and e power alpha. This is common. We can take it common from these two terms. So, and we can write e to the power alpha times C1 e to the power iota beta plus C2 e to the power negative iota beta. Okay, so this solution can be written in this form. Now, this term can be further simplified by using that identity. Here, for in case one, there are two cases here. In fact, in case one, if we assume that C1 is 1 and C2 is 1, again, because C1 and C2 are arbitrary constants, we can take any of their values from the set of real numbers. So for the purpose of simplification of this solution, we assume that C1 is 1 and C2 is again 1. Now, what do we have here? Y of x can be written in this form: e to the power alpha, e to the power iota beta plus e to the power minus iota. Okay. Now we have these two terms, e raised power iota beta and e raised power minus iota beta. And now let's see what is e raised power iota beta. It is, we can write it cos of beta plus iota sine beta. And again, e raised power negative iota beta is what it is, cosine of, in fact, negative beta. This negative beta comes inside here, plus iota sine of negative beta. Now, I hope you know that cosine is an even function and sine is an odd function. So when we use this property of function, this negative term, this negative sign disappears from here. We can eliminate it. But the sign here, the negative sign here in the sine function, it comes out of the sine function because sine is an odd function. Cosine is an even function. So this negative sign disappears. So eventually we have cos of beta here and cos of beta and minus sine beta here. Okay. Now what do we require here? E raised power iota beta plus e raised power minus iota beta. Now adding these two, what do we obtain? If we add these two things, this term and this term, they will cancel out with each other because here we have positive, here we have negative. And what do we obtain here? 2 cosine of beta. Okay, so that term, e raised power iota beta plus e raised power negative iota beta, it becomes 2 cosine of beta. Okay. Now, if we take their negative subtraction, e raised power iota beta and e raised power minus iota beta, what do we obtain? Similarly, we obtain 2 iota sine of beta because we are subtracting those two terms. Now, this 2 and this 2 iota, in fact, we can leave them because these two constants will come into the constants, arbitrary constants of the solution of the equation. So in case of case 2, this term appears in case 2 when we assume that C1 is 1 and C2 is negative 1. So the solution would be y is equal to x, e raised power alpha, e raised power iota beta, minus e raised power minus iota. So this term, we have already written this. It is e raised power alpha into 2 iota sine of beta. So there are two linearly independent solutions because we have chosen the different values of arbitrary constants. If there are two different linearly independent solutions, we assume that this is the first solution, this one, and this one is the second solution. In fact, by using this term, the solution 1 y1 becomes e raised power alpha into 2 sine of, cos of beta, cosine of beta. So we have two independent solutions. They are linearly independent solution. So we can write the general solution by using these two linearly independent solutions. You can check whether these two solutions are linearly independent or not. How? I told you already, by computing the Wronskian of these two solutions, you can prove, you can verify that these two are linearly independent solutions. They form a fundamental set of solutions. Therefore, the general solution, of ODE1 can be written as, so y of x equal to C1 e raised power alpha cosine of beta plus C2 e raised power alpha sine of beta, which further we can take common e raised power alpha outside, and we can write C1 cosine of beta plus C2 sine of beta. These constants which we have removed here, they in fact they can be considered within these constants C1 and C2. I hope you get it. If you have any question, you can ask. So in case of complex conjugate roots, you can write the general solution in this form: y of x is equal to e raised power alpha, where alpha is what? It is the real part of those complex roots. C1 cosine of beta, beta is what? It is the imaginary point, the imaginary number or imaginary part in the complex roots. So this is real part, and this is imaginary part of the complex conjugate roots. So whenever we have complex conjugate roots of the second order differential equation, or we'll discuss the higher order differential equation as well, when we have complex conjugate roots, we write the general solution in this form. I hope you get it. If you have any question, you can ask me. Let's do an example of this case. Whenever we have complex conjugate roots of a differential equation, how do we write the solution? If, for example, we have to solve this differential equation, y 2y double dash plus 2y dash plus y equal to 0. By writing the characteristic equation or characteristic polynomial directly, we can write 2m squared plus 2m plus 1 is equal to 0. So obviously this negative 2 plus minus square root of 4 minus 4 into a into c divided by 2 times 2, which gives us 2 plus minus. Here we have 4 negative 8. You can see that this square root term within the square root, we have a negative sign. So this will obviously give us negative 2 plus minus 2 iota, because we have a negative 4 here. So negative 1, in fact, it is negative 2 plus minus negative 4, which is further what? Negative 2 plus minus, we take negative 1 and square root of 4. Okay. So the square root of 4 is 2, obviously, and we write this thing as iota. So we obtain 2 plus 2 iota divided by 4. And it becomes, we take common 2 from the numerator, and we have obtained negative 1 by 2 plus minus 1 by 2 iota. This is what we obtain. So these are two complex conjugate roots, minus 1 by 2 plus minus 1 by 2 iota. So if we have these two complex conjugate roots, we can write the general solution in that way, which we have discussed earlier. Therefore, the general solution is what? It is y of x is equal to e raised power real part, which is negative 1 by 2, and a constant, maybe C1, cos of what? Imaginary part. Imaginary part is 1 by 2 again, 1 by 2 x. So e raised power minus 1 by 2 x here. You have to write the independent variable as well. There also, previously, we have missed this thing. Let me correct it here. While writing the solutions, the general solution, in fact, we must have x here as well. We write x here. And then the solution becomes here e raised per alpha x and cosine of beta x, e raised per alpha x and cosine of beta x. Here alpha x and beta x and sine of beta x. Because the independent variable, you must have to write it. Sorry for that mistake. So here, whenever we have complex conjugate roots, we write one e raised power minus, real part of x and C1 cosine of imaginary part of x plus C2 sine of imaginary part into x. So this will be the general solution in this case. I hope you get it. If you have any question, you can ask me. There are some, I have given some exercises in my notes on page 21. You can try those exercises for the second order differential equations. In case of any confusion or any difficulty, you can ask me any question in the next lecture. Now, further, for the higher order differential equations, if we have complex conjugate roots, for example, another example of this thing is we need to solve this higher order ODEs with the same, they must be linear, they must be homogeneous with constant coefficients. In case of higher order ODEs, means when the order of a differential equation is greater than 2, then there could be different cases. There might be real roots as well as complex roots. Complex roots may be repeated, real roots may be repeated. In that case, how can we handle or how can we write the solutions, general solution of the equation? It depends. There are several examples here given in my notes. You can see them. Let me try this one. The first one, solve the following differential equation, which is y 4 dash. You can say 1, 2, 3, 4 dash, or simply we can write in this way y 4. It means y 4 dash minus y triple dash plus 2y dash is equal to 0. Now, the equation has order 4, and we need to solve it. After writing the polynomial, characteristic polynomial, the characteristic polynomial can directly be written here in this way, m4 minus m cube plus 2m, okay, is equal to 0. And then we can take m as a common. We can write m cube minus m square plus 2 times equal to 0. Now we have a cubic polynomial here. This m gives us 0 root because this is equal to 0 and this whole thing is equal to 0. This m is equal to 0 is 1 root, and we have a cubic polynomial here. You can see how to find the roots of a cubic polynomial. I hope you have already done this. You can use the factor remainder theorem, which you have already studied in your O levels maybe, or first year in case of FSC. So after finding the roots, we have obtained roots m is equal to 0 and m is equal to -1, and the complex roots, which R. It is 1 plus minus iota. So we have two real roots and two complex roots. In this case, how do we write the general solution? In this case, the general solution is you handle these two real roots in a similar way as we consider the real roots in the case one, because here we have two real roots which are distinct as well. So for the distinct roots, we write y1 of x. The first solution can be written in for this root, which is what? E raised power 0x. This will be your first solution. The second solution will be corresponding to this root, which will be e raised power minus 1x. And third solution will be corresponding to this these complex roots. Y3 of x is what? E raised power real part of x, and cosine of imaginary part is again 1 here. So it is 1x. This will be your third solution. Your fourth solution will be what? E raised power 1x and sine of imaginary part of x. You have to write, in fact, a solution corresponding to each root. And then you use principle of superposition to write principle of superposition to write the general solution. But you can use only principle of superposition if these solutions are linearly independent. Okay, they form a fundamental set of solutions. Okay, they should be linearly, the solution should be linearly independent. How can we check whether these solutions are linearly independent or not? We can use Wronskian. I have already told you. If the Wronskian is non-zero for all these solutions, for all values of x within some specified interval or on the real line, then these solutions form a fundamental set of solutions. Then we can use the principle of superposition according to the theory which you have already discussed in the previous lecture. Now, by using principle of superposition, we can write the general solution. General solution as what? Y of x is what? C1 y1 of x plus C2 y2 of x plus C3 y3 of x plus C4 y4 of x. Okay, and you can just insert the values of it is C1. In fact, e raised power 0x is 1 plus C2 e raised power negative x plus C3 e raised power 1x. You can combine this solution. For the complex conjugate roots, it is e raised power real root times C3 cosine of beta is 1x plus C4 sine 1x. So this will be your general solution. I hope you get it. If you have any question, you can ask. In case of real and repeated roots, for example, here you have -1 2 times. Then I've already told you how to write the solution. In case of real and repeated roots, similarly, if we have repeated complex conjugate roots, we again use the similar logic as we use for the real repeated roots in order to write the general solution of that differential equation correspondingly by writing the solutions in this way. So I have included these kind of examples as well in my notes. You can see those examples. We don't have much time to discuss those examples here. You see them, and you can ask me any question in the next lecture if you don't understand how to write the solutions of in those cases. You can see it once more. Let me clean the board there. Meanwhile, you can see these solutions. If you have any confusion, you can ask me any question. I'm giving you 1 minute. Meanwhile, I'm going to clean these boards. So if you don't have any question, let us start. Next thing which we are going to discuss here. Still, we were discussing homogeneous differential equation of with constant coefficients. Now we are going to discuss higher order non-homogeneous, linear, non-homogeneous, ODEs with constant coefficients. Now, everything is same except now the right hand side of that equation is non-zero. I hope you know how to write the general nth order. This is nth derivative plus an minus 1 yn minus 1th derivative plus so on plus a2 y double dash plus a1 y dash plus a naught y equal to some function f of x, which is not zero. This function is not zero this time. If that function is zero, then we call this equation is homogeneous. So the equation is linear with constant coefficients and non-homogeneous in this case. How to write the solution or how to find the solution of these kind of differential equations? In fact, this general solution of this equation, general solution of this equation, of equation 1, you can say it 1. General solution of ODE 1 can be written as the sum of two solutions, sum of two kinds of solution. One is the complementary solution, complementary integral or solution. We call it complementary solution or complementary integral. Okay. And the second is the important solution, which is particular solution. So this general solution of this equation 1, which is non-homogeneous, it basically is the sum of two kind of solution. One is complementary solution and the other is particular solution. What is this complementary solution? Complementary solution is denoted by It is denoted by yc of x, and particular solution is denoted by yp of x. Then the general solution, in fact, is the sum of these two solutions. Then the general solution y of x is in fact yc of x plus yp of x. It is the sum of complementary solution, or sometimes in some books we call them complementary function, complementary integral. Okay, complementary solution or complementary function, not integral, complementary function. And this is particular solution or particular integral. This is what we call it. So the general solution of one will be the sum of these two solutions. Now, what is complementary solution? C, complementary function, or you can say complementary solution. What is this? Complementary solution where yc of x is the solution of the associated homogeneous ODE. What does it mean? This equation 1 is our main equation. Okay, this is non-homogeneous differential equation. Okay, it has its general solution is the sum of complementary function and particular integral, where complementary function is the solution of the associated, the equation associated to this equation, which is homogeneous part of this equation. Means we just put this right hand side equal to 0. That is, we a n b a n y n y n plus so on plus a1 y dash plus a naught y equal to 0. Means we write the corresponding or associated homogeneous equation, which is same as this equation, except we put the right hand side equal to 0. Okay, exactly same equation. We write the homogeneous part of this equation, means we put the right hand side equal to 0, and then find the solution of this differential equation. The solution of this equation, you can say equation 2, maybe equation of 2 is what? Yc of x, which is called complementary function, and you can write the solution of this differential equation. I think we have already discussed previously how to find the solution of a homogeneous higher order ODE with constant coefficients. We use the similar techniques which we have already discussed in the previous lectures, and we can write the general solution of this homogeneous differential equation. The general solution of homogeneous differential equation is the complementary function, but the general solution of this non-homogeneous differential equation is the sum of complementary function and the particular integral. I hope you get it. If you have any question, you can ask me. Now, how to find the particular integral or particular solution? Second, particular integral or particular solution, whatever it is. Particular integral is denoted by yp of x, and it depends, or you can say the idea of the particular integral is basically based on an educated guess. Motivated by the type of function or type of right-hand side function. Okay. The idea behind the particular writing the particular solution of the given non-homogeneous differential equation is basically we assume some solution or we guess some solution depending on the nature of the right-hand side function. Whatever the right-hand side function is given, we assume the solution by looking at the right-hand side. For example, if we have a differential equation y double dash minus 2y dash plus y equal to maybe 3. Okay. Now, what is the right-hand side function here? Right-hand side function is a constant 3. So complementary solution, you can find it yourself by writing the associated homogeneous differential equation to this differential equation given. Okay, we write, in fact, complementary function is the general solution of this differential equation. The general solution of this ODE is what? It is y of x, which is yc of x plus yp of x. Okay, where yc of x is solution of what? The corresponding or the associated homogeneous differential equation. This is equal to 0. We put this equation equal to 0 and we solve it, we get the complementary function. Now, particular integral, we assume that yp is what? Because the right-hand side function is a constant, we assume that yp is a constant, some constant. You can write a constant a or a constant c or whatever. We usually write constant c's here, so we don't want to repeat those constants here in the particular integral. So we can write some other constant. We usually in books they write these constants which appear in the particular integral. We use capital letters for those constants, for example, a, b, c, or whatever. But you can use whatever constant for your convenience. So we assume that the particular integral is this. If this is the solution, it is one of the solution of the given differential equation, then it must satisfy the given differential equation. So this where a is some constant, a is constant. If it is constant, we need to find its value. Okay, we need to find its value. How to find its value? You put this solution into the given differential equation. You put this solution into the given differential equation, compare left and right hand side, and then find the value of this constant. For example, if we put this here, if we put this solution into this differential equation, y double dash of constant is 0, and the constant derivative of constant is again 0, plus y is equal to a is equal to 3. So this 0, 0 means a is equal to 3. So the value of this constant is 3. So the particular integral solution or the particular solution is what? It is 3. Now, after finding the complementary function, which is the solution of this differential equation, homogeneous part of this differential equation, we can write the general solution by taking the sum of complementary function and the particular integral or a particular solution. You can write its general solution in that way. Okay, so this method for finding the solution particular integral is called method of undetermined coefficients. Method of undetermined coefficients. Okay, method of undetermined coefficients. This method is used for what is used for finding only y p of x. Okay, because y c of x is already known by writing the associated homogeneous differential equation, and then we find y p of x. Okay, after finding y c of x, we can write general solution of the given non-homogeneous differential equation as y of x is equal to y c of x plus y p of x. Okay, I hope you get it. Now, as I told you that the assumption of the particular integral or the particular solution is basically purely dependent on an educated guess motivated by the right-hand side of that function. Now, I have listed down the types of the particular solutions of differential equations in case of the different right-hand sides. Okay. Yes. But remember that note, or you can have a remark here. This method is not always helpful to find the particular integral. This method only works when we have some specific kind of right-hand side functions. For example, this method, you can say this method works only if the right-hand side function f of x is of the form Maybe what are the forms of the right-hand side functions so that we can find the solution of the given differential equation, non-homogeneous. The right-hand side function could be a constant function, means constant function. Second, a polynomial function. Number three, exponential function. Number four, sine or cosine function. Number four is either or both, either sine or cosine function. This is strictly sine or cosine. It cannot be tan. Okay, it cannot be tangent function. It cannot be cosecant. Eventually, it becomes 1/2 sine, but 1/2 sine is not also allowed. The right-hand side function should be one of these kind of the functions or their sums or their products. Okay, the right-hand side function can involve these functions or their sums or their products as well. Then we can find the solution of the particular integral or the particular solution of the non-homogeneous differential equation. And the particular integral is again can be computed by starting with an assumption for the solution of a particular solution by starting with an educated guess motivated by the right hand side function, and then which contains certain coefficients, which contains constants. And later on, we need to find those constants. And that is why we call it method of undetermined coefficients. And for each kind of these functions, there are standard educated guesses, which I have listed down here in my notes. You can see them. And okay, before writing those functions, let me tell you that this method works only if the right-hand function is of this form. Otherwise, this method is not useful, or this will not help us to find the solution of the particular solution of the given differential equation. Okay. This method fails. You can say that this method fails if the right-hand side function, RHS function, f of x, is of the form, or it contains maybe 1 over x, or 1 over polynomial of functions, or the quotient function. You can say that polynomial of x, some quotient of polynomials. It contains log of x. It contains any other trigonometric functions, tangent of x, or combination of these functions. In that case, the function, this you can assume that it could be x over x squared plus 9x plus 2. Okay, or you can say that the right-hand side function involves the inverse functions. Then this method doesn't help us to find the particular solution. I hope you get it. If you have any question, you can ask me. Now, the educated guesses in different situations are, we can write, let me write it here, not here, somewhere. Now, we have educated guesses in different situations. Number one, if the right-hand side is constant, then we assume the particular solution as a constant. I have already told you. Number two, if the right-hand side is a polynomial, it could be polynomial of degree 1, degree 2, degree 3. In that case, we write the polynomial accordingly. If the polynomial of degree, if the right-hand side is a polynomial of degree 1, then the particular solution should be a times x plus b, which is a polynomial of degree 1. If the right-hand side is a polynomial of degree 2, then the particular integral or the particular solution should be a polynomial of degree 2, which is ax squared plus bx plus c. You can see that in the polynomial of degree 1, we have written these coefficients a, b, which are constants. Here a, b, c are constants. And so on. If the polynomial is of degree 3, we write the particular solution as a polynomial of degree 3 with some coefficients a, b, c, d. These are coefficients a, b, c, a, b, c. These are unknown coefficients or undetermined coefficients. So by inserting this particular solution into the given differential equation, we try to find the values of these constants, undetermined coefficients. That is why we call this method is a method of undetermined coefficients. So these the second case. Number three is if the right-hand side function is exponential function. If the right hand side is a function, exponential function, then we write particular integral in the form of exponential function, some constant time exponential of the same coefficient here, alpha x, where alpha is the same as the alpha given in the right hand side. Okay. In case of sine or cos, in case of sine or cosine function, the particular integral is assumed to be yp of x is always assumed to be a times cosine of alpha x plus b sine of alpha x, where alpha is the same as given in the question, okay, given in the right hand side of the function, where a and b are unknown coefficients. Here a is again unknown, undetermined coefficient. So by inserting all these particular solutions in different cases, whatever the case is given, whatever the right hand side is given, we insert these particular integrals into the given differential equation and try to find the values of these undetermined coefficients. Okay. Now, these were functions, individual functions. We assume the particular solutions in this case. Now, when we have combination of these functions, means the combination could be the sum of these two functions, any of these two functions, or the right hand side could be the product of any of these functions. Product could be the product could involve two functions or more than two functions. In that case, we write an educated guess accordingly. How do we write that guess? Let me, for example, or you can say that further guesses, further. In case of addition of two functions, in case of addition of these two kind of functions, for example, the right hand side f of x is the sum of first degree polynomial, maybe, for example, if it is x e raised power 3x, for example, right hand side. Now the right hand side function is the product of two functions. This function is a polynomial of degree 1, okay, and this function is an exponential function. How do we write the educated guess? How do we write p of x? Why p of x? It should be ax plus b times e raised power 3 alpha. This should be the educated guess of the particular integral. Why do we write it? Because for the polynomial of degree 1, we write this guess, and for the exponential, we write a e raised by alpha x. But if we write a here, a will eventually be multiplied here, and it becomes a new constant here, a new constant here. So we eliminate this thing. For example, if we write a here as well, or c e raised power 3 alpha, the constant should be different. The c will be multiplied here and here. AC and BC, those will be new constants. So we do not need to write here a constant. Okay. Now, sorry. It's a product, not addition. Product of these functions. If we have addition of these two functions, means right hand side is written as x plus e raised power x, e raised power 3x. Sorry, here we have x, not alpha. Then we write ax plus b for this polynomial of degree 1, plus for this exponential, we write another constant, e raised power 3l, e3x. So this is how we can write the educated guess for the particular integral. By inserting this solution by p of x into the given differential equation, we try to find these constants A, B, C, and so on. Similarly, if we are given here some maybe exponential function times sine of 3, maybe we can write some here, 5x. Now, the right-hand side function is exponential times a trigonometric or the sine function. In this case, the particular solution, which we assume it should be e raised to power 3 alpha times a sine 5x plus b cosine of 5x. Okay, this should be the educated guess. In case of sum of these two functions, sine of 5x plus e raised to power 3x, in that case, the solution, assumed solution should be a times sine 5x plus b times cosine 5x plus, we treat it differently and we treat it differently, c e raised to power 3x. So this will be your particular solution, assumed particular solution. After guessing the particular integral, we put this integral into the given differential equation and try to find the undetermined coefficients by comparing left-hand side and right-hand side. Okay, do not mix the left-hand side and right-hand sides. You cannot take any term of the left-hand side to the right-hand side or from the right-hand side to the left-hand side. Okay, because later on you have to compare these two sides in order to find these undetermined coefficients. I hope you get it. We'll do now examples of these things. But before doing the examples, let us discuss the principle of superposition in case of non-homogeneous differential equations. In case of these non-homogeneous higher order ODEs, principle of superposition is different for homogeneous and non-homogeneous. Okay, now we are going to discuss principle of superposition for non-homogeneous ODEs. Okay, remember this. For complementary solution, we use the same principle of superposition as we use in case of homogeneous ODE, because the complementary solution is we write that solution for the associated homogeneous differential equation. And for the homogeneous differential equation, we use the principle of superposition for the homogeneous ODEs. But for the non-homogeneous ODEs, we use the principle of superposition only for the particular integrals, for the particular solutions. Okay. In case if we have the left-hand side should be an operator L of y, and the right-hand side is f of x. I told you previously that we can write the general nth order linear ODE in this form, L of y, where L is the linear operator, which I have already told you. Now, the important is the right-hand side function. Okay, for the right-hand side function, चलें मैं लिख देता हूँ आपके पास. यहाँ पे क्या होगा? an yn dash plus an minus 1 yn minus 1 dash plus 1 plus a1 y dash plus a naught y equal to यहाँ पे fi of x. Okay, where fi we have a lot of means I could vary from 1 to k. We have k such differential equations whose right-hand sides are different only, but the left-hand sides are same. Okay, we have k nth order differential equation, linear with constant coefficient, non-homogeneous, k fi where I is from 1 to k. We have k differential equations whose left hand sides are same, are identical, but the right hand side is different. Okay. Then we have ypi of x. Okay. Then ypi of x are particular solutions of these k equations. These you can say star this of star equations for each I. Okay. For each value of I, we have one particular integral. Okay. Particular solution. Okay. Then the general solution. Sorry, not you can say that. Then by the principle of superposition, then by the principle of superposition, yp of x, the general yp of x is what? Yp1 of x plus yp2 of x plus so on plus ypk of x will be the solution of this principal position will be the solution of let me write it over here, will be the solution of a n y n plus so on plus a1 y dash plus a naught equal to f1 of x plus f2 of x plus so on plus fk of x. Okay, means these are individual k equations where we have f1, f2, f3, so on, fk. Okay, right, k right inside functions. If ypi for each I are the individual particular solutions of all these equations, then the principle of superposition says, it tells us that the sum of particular solutions will be a particular solution of one differential equation whose right hand side has the sum of all these functions. Okay, this is what principle of superposition tells us here in this case. I hope you get it. If you have any question, you can ask me. Now, how to use it? Let me come to the other board. Meanwhile, you can see it. Let me clean the other board. You can see it. If you have any question, you can ask me. Why this is important, why this superposition principle is important, let me show you why do we need it here while solving the differential equations. For example, if we are given a differential equation of this form, yes, this one. Example. we have to solve the following differential equation, which is y double dash minus 3y dash plus 4y equal to negative 16x squared plus 24x minus 8. This is the first differential equation. The second is, again, the left hand side is same, but the right hand side is 2 e raised power 2x. Okay, these are two differential equations. We assume that the particular solution of this differential equation is the right hand side function, the second order polynomial degree, second degree polynomial. We assume that this is ax squared plus bx plus c. And then by inserting this particular integral into this differential equation, we can find these undetermined coefficients and we can obtain the solution. After doing this, we obtain that this the solution is negative 4x squared, BCR0. And assuming that the particular integral of this is yp1, this is yp2. The particular integral of this equation is, we assume that it is a e raised power 2x. By inserting this solution into the given differential equation and computing the value of these coefficients, we obtain that this is 1 e raised power 2x. The value of a is 1 here in this case. Okay, or you can change the names of coefficients. You can write here c, because you have already written a, b, c. You can write here some coefficient d. Okay, after finding d, we can write the particular integral, this one. Okay, these are two particular solutions of two different differential equations, but the left hand side of these two differential equations is same. Then by principle of superposition, then by principle of superposition, the general or the particular solution yp of x is what? Yp1 of x plus yp2 of x, which is what? It is negative 4x squared plus e raised power 2x, is the particular solution of the ODE, the same ODE, y double dash, left hand side is same, plus 4y equal to the first function, negative 16x squared plus 24x minus 8, the first, plus the second is 2 e raised power 2x. Okay, so the sum of these two particular solutions will be a particular solution of this differential equation, which has the sum of these two right hand sides of those two differential equations whose left hand sides are same. And why this is important, and this basically helps us to solve this equation. For example, if we are given this kind of differential equation where the nature of right hand side function is different, means we have a polynomial function plus an exponential function. Okay, then we can split up this differential equation into two differential equations. One having this right hand side function, which contains only a polynomial function, and the other which contains the exponential function. Now, by splitting this one differential equation into two differential equations, we can easily write or find particular solutions of these two individual differential equations. And then we can take the sum of particular integrals of these two differential equations to get the particular integral of this differential equation. This basically helps us to simplify the calculations of undetermined coefficients. Okay. Now, if you see that we assume the solution this plus this, and then we insert the solution into this differential equation, this will complicate our calculation of the undetermined coefficients. Okay. The principle of superposition help us to to divide the differential equation into various differential equations. If we are given three kind of functions here, then we can divide the equation into three differential equations, and then separately we can find the particular solution of each differential equation, and then by using particular principle of superposition, we can sum up the particular solutions in order to get the particular solution of the given differential equation. This is why principle of superposition is important here, and it helps us to simplify the calculations, okay, to find the undetermined coefficients in these cases. I hope you get it. If you have any question, you can ask me. In the next lecture, we'll do a couple of examples of these kind of differential equations, and then we'll move towards the application of second order differential equations. I hope you get it. If you have any question, you can ask me. Otherwise, I'm going to stop it here for today.